Welcome to another edition of CSEC Physics Simplified. In this lesson, we will be looking at momentum, and once again, I am Sir Damien LaRose. In this lesson, we will be looking at momentum overview, or we can say the momentum principle, and conservation of momentum. To introduce momentum, we will go with what we are very familiar with here in the Caribbean, and as we look at our television, what we would normally hear. And so we would hear the sports announcer saying, going into the tea break, the West Indies have the momentum. The headline declares, Chicago Bulls gaining momentum. Or we may see, the coach pumps up his team at halftime saying, you have the momentum. The critical need is that you use that momentum and bury them in this third quarter. Momentum is a commonly used term in sports. A team that has the momentum is on the move and is going to take some effort to stop. A sports team that is on the move has the momentum. If an object is in motion, that is, it is on the move, then it has momentum. Momentum is a physics term, and it refers to the quantity of motion that an object has. Momentum can be defined as mass in motion. All objects have mass. So if an object is moving, then it has momentum. It has its mass in motion. The amount of momentum that an object has is dependent upon two variables. One, how much stuff is moving, and two, how fast the stuff is moving. Once again, the amount of momentum an object has is dependent upon these two variables. First, how much stuff is moving, and second, how fast the stuff is moving. So here we have it. Momentum is mass in motion. This is what we need to remember. Momentum is mass in motion. Any mass that is moving has momentum. Momentum depends upon the variables mass and velocity. For our equation, momentum equals mass multiplied by velocity equals mv. For an example, we are going to calculate momentum. And in this example, a van with a mass of 500 kilograms traveling at a velocity of 40 meters per second. What is the momentum of the van? So we must have our data, mass, (500 kilogram) and velocity, (40 meters per second). Now momentum from our equation, we have it as mass multiplied by velocity and key to remember is that mass is measured in kilograms, whereas velocity is measured in meters per second. And so now if we should put our variables, we have 500 kilograms multiplied by 40 meters per second, and this would give us 20,000 kilogram meters per second. So here we have the unit of momentum is kilogram meters per second. To continue with our principle, we are going to look at an elephant. And it goes by, if an object is at rest, it's how large its mass. Momentum is not the same as inertia. Remember that when we were looking at Newton's first law of motion, inertia comes into play, which is the resistance of an object to move. This is not the same as the resistance of an object to move. An elephant has a large mass. If the elephant is not moving, it has zero momentum. So there we have it. Momentum is equal to mass. In the case of the elephant is large, so there is a large mass, but velocity is zero. Let us continue using the school bus. A bus can have a large momentum, even if it is moving very slowly, because it has a large mass. Notice that we have the school bus, and the arrow indicates that its velocity is small. And so a large mass with a small velocity would give us a large momentum. And so even if the school bus is moving slow, or if we have a truck, which is also large, is moving slow, do not get in the way of a moving object, especially if it is large as a school bus or a truck, because it would have a large momentum and you can be hurt. In this instance, we are using a small object. A bullet can have a large momentum, even if it has a small mass, because it is moving at high velocity. And so, with a small mass, with a high velocity, would give a large momentum. And so here we would see it, that in the movies, even though we cannot see the bullet, and we know that the bullet is very small, we still see the actors being pitched backward when being shot. And that is because the small mass with high velocity or a large velocity would give a large momentum. And because the momentum is large, the actor would go backwards. And that is a reality. In the conservation of momentum, we would normally use the Newton's cradle. And here we have it. Notice that momentum is being transferred from one of the pendulum bulbs to another. And this is basically what conservation of momentum is. Momentum is being transferred from one object to another when it collides. We are going to be looking at momentum examples with the conservation of momentum in the next segment of our lesson. The law of conservation of momentum. It states, for a collision occurring between object 1 and object 2 in an isolated system, the total momentum of the two objects before the collision is equal to the total momentum of the two objects after the collision. To simplify it, that is, the momentum lost by one object is equal to the momentum gained by another object. And so we can say that momentum before collision equals momentum after collision. The letter P, that is common P, is used to denote momentum. And so momentum in the first object, that is before collision, plus momentum of the second object before collision, the total momentum, hence we place them in brackets, is equal to the momentum of the first object after the collision plus the momentum of the second object after the collision. So we see total momentum of the two objects before collision is equal to the total momentum of the two objects after collision. And that is what we mean when we say conservation of momentum. To visualize the conservation of momentum, first you must understand is that momentum can have two natures. One if it is elastic, and 2 if it is inelastic. When we speak of elastic collisions, because remember, momentum deals with collisions in the conservation of momentum. If the collision is elastic, well then we say that no energy is lost. There is no loss of momentum. If the momentum is inelastic, that is, the collision is inelastic, well then momentum is lost, or we say energy is lost. When we refer to elastic collisions, we are speaking about an isolated system where there is no factor influencing the momentum or the collision. So with the two, elastic and inelastic collision, they both can move as one body, that is, the two objects can move as one body, or they can move as separate bodies. They can move apart as one. When they are moving as one body, they can move in one direction. And when they are moving as two bodies, they can move in opposite direction, or they can move in one direction. So here is where we simplify what happens with momentum conservation. From the previous chart, we are going to be looking at a few animations to help us understand what is going to happen with the conservation of momentum in 4 different scenarios. We have them as A, collision in the same direction, collision in the opposite direction, C, small momentum collides with a large momentum, and D, large momentum collides with a small momentum. Here, we are looking at collision in the same direction when we have a large momentum represented by the truck collides with an object that is smaller. Notice that conservation of momentum says that momentum before collision is equal to momentum after the collision. And for the truck, it had a total momentum of 60,000 kilograms meters per second, whereas the car's momentum is 0 because it is stationary. After the collision, the truck's momentum is 45,000 kilograms meters per second, and the car's momentum is 15,000 kilograms meters per second. Notice that they stuck together in the same direction. And if we should add 45,000 plus 15,000, that would give us 60,000 kilograms meters per second, and we can therefore say that momentum is conserved. In the second instance, we have a head-on collision. Both small and large momentum are headed in the opposite direction, and when they are headed in the opposite direction, we normally would use a negative number to represent one of them. The car has a positive 20,000 kilogram meters per second, whereas the truck has negative 60 kilogram meters per second. And if we should add 20,000 plus negative 60,000, we would have negative 40 kilograms meters per second. And so you may be wondering, why is it that we're speaking about negative? When we begin to look at motion, notice that motion in the rightward direction or in the forward direction is given a positive value, and motion going to the left is given a negative value. Hence, the truck having a negative momentum. At the end of the process, notice that both truck and car are going in the negative direction. The car has 10,000 kilograms meters per second, whereas the truck has minus 30 kilograms meters per second. If we should add the two, minus 10,000 plus minus 30,000, that would give us minus 40,000 kilograms meters per second. And here we can see that momentum is also conserved. But notice both objects goes in the direction of the larger momentum. Let me repeat that. Both objects will continue to go in the direction of the larger momentum. Small momentum collides with the larger momentum. In this case, the small one is behind and the larger one is front. Initially, notice that we have a momentum of 20,000 for the car, and the truck is stationary, it isn't moving. So at the collision, notice that momentum is conserved and they are both moving in a different direction. The car begins to go to the left and the truck is going forward. Initially, we have 20,000 kilograms meters per second. After the collision, the car has minus 10,000 kilograms meters per second, whereas the truck has 30,000 kilograms meters per second. And so if we should add minus 10,000 plus 30,000, we end up with 20,000 kilograms meters per second as the total momentum. So once again, momentum is conserved because we have before the collision 20,000 kilograms meters per second, and after the collision we also have 20,000 kilograms per second. Okay? And finally, we have D, where there is a large momentum collides with the smaller momentum. Overall, notice that there is 60,000 kilograms meters per second as the momentum. Afterwards, both objects continues to move in the same direction, even though they did not stick together. However, after the collision, the truck's momentum is 30,000 meters per second. The car's momentum is 30,000 meters per second. And notice that the car's velocity is much greater than the truck. So whenever we have a large momentum colliding with a smaller momentum, we would normally see an increase in velocity that is greater than the larger momentum. At the end of it, 30,000 kilograms meters per second for the truck and 30,000 kilograms meters per second for the car would give us 60,000 kilograms meters per second. Momentum before the collision is equal to momentum after the collision. And here we have the various scenarios of momentum being conserved. This brings us to the end of our lesson on momentum. The main points, as we would have them, momentum is mass in motion. Momentum is determined when a mass is multiplied by its velocity. Momentum can be either elastic or inelastic. The unit of momentum is kilograms meters per second. In momentum conservation, when one body gains momentum, the other body loses momentum. This brings us to the end of another session of CSEC Physics Simplified. Join us again for another edition of CSEC Physics Simplified as we continue to learn physics.